Let's start the last sub-article of gravitational acceleration, in which we are discussing the variation coming in the effective gravitational acceleration with latitude due to Earth's rotation. Now, we have seen about the word latitude in the previous article or the second sub-article of gravitational acceleration, but what is the actual definition of that? So, the angle made by the line joining a given place on the Earth's surface to the center of the Earth is called the latitude, and it is denoted by delta of that place. And here the line joining a given place on the Earth's surface to the center of the Earth with the equatorial line, not a simple center. So this is the definition of latitude. So it is basically an angle, and hence for the equator the latitude lambda is 0 degree, and for the poles the value of lambda is 90 degree. Now we will see one arrangement, and from which we are going to discuss about the calculation of gravitational acceleration. So here you can see this figure, and we have to find out the latitude of the place P on the earth, means of this point, and for that I am giving my latitude at point P is nothing but angle POE according to the definition, and at this position we have to consider a particle which is having mass m. And so we can say the mainly two forces are acting on this particle. So which are the two forces? This is important. So first kind of force is Earth's gravitational force. That is mg, and you can clearly see from the figure the direction OP or PO. So this is basically the direction of force, and it is inside the Earth's surface. But what is the second kind of force? And for that we consider over here the rotation of the Earth. And also the earth has an acceleration due to the rotation, and so the particle which is on the earth's surface is in the accelerated frame of reference. So particle at point P is in the accelerated frame of reference. And due to this, we consider that at this point the acceleration of the frame of reference is equal to the centripetal force Fp, means V square over R, and the direction, if you see from the figure, here the direction will be in Pm direction, and it is also inside the earth surface because the outside force is always zero, and hence we have to consider this fictitious acceleration, and the fictitious force means mv square over r in the opposite direction. So which you can consider as opposite direction? See, mpq direction. So v square over r and mv square over r both are in mpq direction, where v square over r is in pm ray direction and mv square over r is in pq ray direction. And the component of this force, in which direction you can take the component? See, this is the MPQ type of direction. So in PR ray, we can take the components of force F. Therefore, the component of this force is in PR direction, and the component is given by mv square over r cos of delta, where delta is the latitude, and we can easily find out delta by just measuring the angle. So this kind of forces, but what is the effective force? These are two different forces, and therefore my target is to find out effective force, because I have used the word in the starting or title of the theory as effective gravitational acceleration, and hence the effective force on the particle having mass m and which is at point P is given by mg dash, which is equal to the difference between the two kinds of forces, that are mg minus mv square over r cos of delta, and therefore here I can consider g dash as effective gravitational acceleration without consider the rotation of the earth. So see, this is only related to a stationary kind of motion, linear motion, not rotation is considered over here. And therefore I can get common this m value from both the sides. So this equation will look like G dash is equal to G minus V over R cos of delta. And remember, here V is nothing but the velocity of particle, and it is related with the angular velocity. V is equal to R omega, where omega is the angular speed, and this speed is you have to consider as for Earth. So this is angular speed of the Earth. So substituting this equation or this result in equation number 1, therefore G dash is equal to G minus V square over R. So instead of V, now I am putting R omega whole square over R cos of lambda, which is equal to G minus R square omega square divided by R cos lambda. So 1 R will cancel out. Therefore, G dash is equal to G minus R omega square cos of lambda. From the figure, if you can see, I am giving you the figure again. So here the distance, which is MP, is given by, at R is equal to MP, the radius of the earth will come into the formula. So that is Re cos of lambda, and hence I can substitute this value in the above result. Then my effective gravitational acceleration will become G minus Re omega square cos square lambda, and this is my result number 2. And I can take G common from the right hand side of equation number 2, then I will get G dash is equal to G into the bracket 1 minus Re omega square cos square lambda divided by G. And this is also one important relation, that is relation number 3. And with this relation, the gravitational acceleration is changing according to the latitude change due to Earth's rotation. Now at equator, we have considered delta is equal to 0 degree, and therefore cos delta is equal to 1, and therefore the value of G dash is equal to G minus Re omega square cos square lambda. So 1 square is 1. So this is showing us the minimum value of effective gravitational acceleration. So this is the minimum value. So what should be the maximum value? So the maximum value can be obtained at the poles. At the poles, the value of lambda is 90 degree, and therefore cos delta is equal to 0, and therefore the effective gravitational acceleration is G minus Re omega square into 0. Therefore G dash is equal to G, that is the maximum value of effective gravitational acceleration, and in between the values will keep on increasing as far as the cos function is concerned. Now we will solve one illustration related to this particular article, and then we will see the another approach related to the gravitation, and that is gravitational intensity.